We have looked at electric fields in earlier grades, but let's just recap a whole lot of stuff that we can almost take for granted that you already know. Objects that lose electrons become positively charged. Objects that gain electrons become negatively charged. We know that. Like charges repel each other, just like poles of a magnet, and opposite charges attract each other, just like opposite poles of a magnet. If I rub two objects together with friction, the two objects will then usually transfer some electrons. So something might become positively charged and another thing might become negatively charged. And we can take a PVC rod and you rub it with a flannel cloth, and then one of them gains and one of them loses. They need to tell you a little bit more about that. You would need to know exactly what the nature of those were. You don't have to learn your PVC rods and your flannel cloths off by heart at all. Neutral objects are attracted to charged objects because the electrons can be moved on the neutral object. Let me just show you an example of that quickly. So if I have got, for example, a positively charged rod over here, and I have got a little piece of tissue paper over here that's neutral, what will happen is it will almost create a dipole. The electrons on this piece of tissue paper will be attracted to the left. And even though overall this is neutral, it will still land up having a slightly negative side and a slightly positive side. And then you will have a force of attraction between the positive and negative. So neutral objects are attracted to charged objects. By definition, an electric field is a region of space in which an electric charge experiences a force. Very much like gravity. I mean, around the Earth, in this region of space, there is a region of space in which objects are attracted to the Earth in a gravitational field. And the very same thing is true in an electrical field. It's a region of space around a charged particle that would experience that if I put another little charged particle in there, it would experience a force. The direction of the electric field at any point is the direction that a positive test charge would move. So if something is positive, it will obviously move towards negative. So that is the direction of an electric field, from positive towards negative. Here are a bunch of field patterns. This would be a point charge over here. And then, as you can see, the field pattern around it is a radial field pattern. A field about two like point charges are going to land up being like this, where you'll notice the pattern will look something like that. And I'll show you why that comes to pass in a minute. Let's just look at all the shapes. If these were opposite point charges, you land up with fields that seem to almost like connect with one another. Between two parallel plates, you get a uniform field, and it's always from the positive to the negative. And on the inside and the outside of a hollow object, a hollow round object would be just like the Earth, really. It would look a lot like the point charge, but just a whole lot bigger. Now, I want to just investigate these two a little bit more. Let's say I had a positive point charge here and a positive point charge here. And there's a radial field around each of them. And it's from positive towards negative. So it's away from the positive. So what happens at this intersection? You can see quite clearly that these two will cancel each other out. So what you land up with is a field that takes on this shape over here. The exact same thing would happen if I were to make these negative charges, except that all my arrows would be pointing from positive towards negative, but the shape of the field would be exactly the same. But however, what if I put a positive and a negative charge? Alright, you land up with something that looks a bit like this. Now, I just want to highlight the fact that when you draw these diagrams, you need to draw them with a ruler. Your field lines need to join beautifully and perfectly and all of that sort of thing. I'm just demonstrating over here. Now, over here you have got the positive, which is going from positive to negative, so it's away. And over here you've got your negative, so it's going from positive to negative, so towards. So what you land up with is a reinforced electric field between these two charges, and they actually land up connecting with one another, and you land up with that type of a pattern happening. Field lines are considered to run from positive towards negative. An electric field line is simply a line of which the tangent at any point gives the direction of the electric force on on a small positive charge placed at that point. Field lines, you always draw them perpendicular to the surface. They don't ever intersect or touch one another. They are close to one another when you've got a strong electric field, and they are far away when you've got a weak field. They run parallel when the field is uniform. Uniform means it's even Stevens. They're from positive to negative, and they are not real. They are just a diagrammatic representation of a field. You do not really have field lines. They're merely there to try and give us a diagrammatic representation. They're on the paper, but a real field is in a three-dimensional space all around the charged object. These are how we would draw those field lines nicely. As you can see, from positive point charge would be repelled away. Notice how the field lines are getting further apart. There they're close together, there they're far apart. That means the field is getting weaker as you go further from that point charge. Two like charges are going to land up with the space in the middle because of the interference of their field lines. Unlike charges will connect with one another, and they will go from positive towards negative. A uniform field from positive towards negative, and notice that those are evenly spaced lines to show the uniformity. At the edge of the plate, you land up with a slight curve to those lines because it's now not 100% uniform just around the edge of the plates. These are the ideal field patterns that you would need to learn.